My name is John Stanton from the University of Washington, and what you're in now is the Structures Research Lab at the University of Washington. And we've been helping Tom by doing some of the testing on his system while he's been developing it. What we're really trying to test is the ability of this wall to resist horizontal forces. And as you can see, the wall is held at the bottom by a series of bolts going down into the floor at the side here, and these pieces of timber on the floor. So they simply stop it moving backwards and forwards at the bottom. At the top of the wall, it's attached by that piece of steel to the big black hydraulic jack which is attached to the wall, and that jack will move in and out and therefore push the top of the wall backwards and forwards in a left to right sense. And that will simulate the forces which would go on during an earthquake in a real building. And the question at issue here is how big are the forces and how big are the movements that we can apply to the wall without the wall breaking down seriously. There are a few other systems for doing the same job, and they, for example, either might not have a rod at all, but they might try to resist the uplift by using the timber studs here as the tension part, and then you'd have a connection from here down to the floor, and another connection from there to this floor, and another connection as you go on up. And that system, or systems like that, mean that you have an awful lot of little pieces of metal connecting a lot of individual pieces of wood together, and they offer the possibility, which is not offered here, of a localized failure of one of the little pieces, one of the connector pieces. And the second thing that happens is that each time you connect two pieces together, then there is some local flexibility that happens there. There's a little bit of play. And so those systems would have somewhat more play in them than this one will. The second possible approach would be that if you had a rod going up like this one and you just put a regular nut on the top here, that would give you the advantage of not having a whole lot of small connectors connecting lots of different pieces. But as Tom pointed out, it would have the disadvantage that as the wood dries out, which inevitably it will once the building is enclosed and you switch on the air conditioning, etc., the wood will dry out and it'll then shrink. And over the height of a 4-story building, the shrinkage may be somewhere in the order of 1 or even 2 inches. And so the top of the building will sink down. The steel does not shrink, and therefore you're left with a 1 or 2 inch gap between the nut and the plate if you do not have a shrinkage compensating device like this one here. What that means then is if you arrive with an earthquake and you have a gap in here between the nut and the plate, then what will happen is that the wall can rock quite a long way before the nut even makes contact with the plate. So it means that the system is a lot more flexible and it'll have a lot more movement in it, and therefore you'll suffer much more damage in the building. So having a shrinkage compensating device of this sort makes a big difference in terms of the amount of damage you could expect in the building.
There are also some new devices on the market in Western Washington intended to help us cope with earthquakes. King 5's Kathy Kiyomura has details.
The developer of the Bay Villa condominiums in Alki believes the 5-story building could be one of the most earthquake-resistant structures around. The building contains new devices called the Earthbound System. Its inventor says the system helps to hold a wood-framed building to its foundation in an earthquake. Today, the device was tested for observers at the University of Washington. The wall is shifting side to side by about 3.5 inches. The test shows the effects of a major earthquake on a standard weight-bearing wall using the Earthbound system. The device, developed by Inquest Engineering of Woodinville, lessens the stress on a building during an earthquake, while compensating for the settling and shrinkage common in wood structures.
1 or 2% is the kind of numbers that you're normally looking for in a pretty severe earthquake. We're now at 3.5%, so we're at least twice and probably 3 times what you'd be looking for in most very severe earthquakes.
So this is doing its job plus?
Plus in spades.